Today, we're diving into a pretty wild idea. What if the future of AI has less to do with brilliant new code and more to do with a head-on collision against the laws of physics? We're going to break down a framework that completely redefines the absolute physical limits of computation. Okay, so let's just jump right into this weird paradox. On one hand, AI seems like it's becoming this unstoppable, godlike force. But on the other hand, we keep hearing that Moore's law is dead, that progress is slowing down. What if the real problem isn't just about making smaller, faster chips? What if the problem is the actual, literal, physical space that our computers have to exist in? To really get a handle on this physical wall, we first have to understand the blueprint that computer science has been using for, the last 50 years or so. And it's a blueprint that imagines a perfect world of pure logic, one that's totally disconnected from physical reality. You know, this traditional model is completely mathematical. Computer scientists have all these names for it, like NC and AC, but don't worry about the jargon. The best way to think about it is like a perfect city plan drawn on a piece of paper. It looks amazing, but it totally ignores things like traffic, plumbing, gravity, or the fact that you can't just build a skyscraper 1,000 stories high on a tiny patch of dirt. And this is where that contrast becomes so stark, it's almost funny. On the left, you've got the fantasy computer from those paper models. Signals travel instantly, connecting things costs nothing. But on the right, well, that's the messy reality of the computer that's actually in your hand. It's stuck with the speed of light, and every single wire, every connection takes up space, sucks up energy, and spits out heat. So, what happens when that perfect paper blueprint slams headfirst into the real world? Well, it smashes into 3 unavoidable laws of physics. And these aren't just suggestions, they are the fundamental, unbreakable rules of our universe. The first and most critical idea to get your head around is something called the causal region. Okay, imagine a calculation starts at a single point. As time takes by, the information from that calculation can only spread outwards at the speed of light. It creates this expanding bubble of influence. Everything that computation does has to happen inside this bubble. And that leads directly to our first big constraint: volume. You can only cram so many processors into that expanding 3D bubble. Now, the math shows that the volume of that bubble grows with the cube of time. So if you double the time, you get 8 times the space. That sounds pretty good, right? But it's only half the story. Here's constraint number 2, and honestly, this is the real killer. All the data, all the information has to get in and out of that bubble through its surface. But the surface area only grows by the square of time. So double the time, you only get 4 times the surface. You see the problem? Your internal processing power, the volume, is growing way, way faster than your ability to actually feed it data through the surface. It's a massive communication bottleneck. And finally, as if that wasn't enough, there's heat. There's this thing called Landauer's principle, which basically says that whenever a computer erases a bit of information, which is something it does constantly, it generates a tiny bit of heat. And where does all that waste heat have to go? You guessed it, it has to escape through that exact same limited, 2-dimensional surface area, creating yet another bottleneck. So we're faced with these 3 huge physical walls: volume, throughput, and heat. Because of this source material here proposes a new, much more realistic rulebook for figuring out what's actually possible. And this is the brilliant new framework. It's called RCD, which stands for Realizable Circuits in D dimensions. But forget the jargon. It really just boils down to 2 incredibly simple rules based on geometry. Rule number 1, the size constraint. Your total computing power is limited by your volume. Rule number 2, the width constraint. Your ability to talk to the outside world is limited by your surface area. That's it. It's that simple and that profound. Now here's the really amazing part. Once you have this new, physically grounded rulebook, you can actually calculate the absolute universal speed limit for any possible computation in our universe. And the result is it's shocking. Just look at the bottom row of this table. In an ideal infinite dimensional world, the fantasy land our old theories lived in, the time it takes to compute something is practically instant. But now look at the row for our real 3-dimensional world. The absolute best we can ever hope to do is a speed proportional to the square root of the input size. Let me put that in perspective for you. To process, say, 1 million items, the ideal model takes about 20 steps. Our physical reality? It takes 1,000. That is a massive, massive slowdown. And it's dictated purely by the geometry of the universe we live in. Okay, so this isn't just some abstract theory for physicists to argue about. This directly explains the very real scaling problems we're seeing right now in the most advanced AI models on the planet, like the ones that power ChatGPT. Let's look at the attention mechanism. It's basically the secret sauce in models like GPT. To understand a sentence, it allows every single word to look at and connect with every other word in that sentence, all at the same time. Now, as you can probably imagine, that's just a total explosion of communication. It's the perfect example of a process that is incredibly heavy on communication. And this is exactly where it all comes together. That attention mechanism runs smack into the surface area bottleneck we were just talking about. All that back and forth communication between the different attention heads is physically limited by that throughput constraint. It means that just adding more processors gives you diminishing returns. You literally cannot beat the geometry of space. And this provides a physical explanation for why just making AI models bigger and bigger isn't a sustainable path to real intelligence. So, what does all this mean for the future then? Well, it requires a really profound shift in how we think about the very idea of computation. What's so elegant about this whole framework is that it shows our old computer science models weren't wrong exactly, they were just a special case. They were a non-physical ideal, where space and geometry just didn't matter. They were the view from some imaginary infinite dimensional world. And that brings us to the core takeaway here. We have to stop thinking of computation as this abstract logical thing that just happens in a void. We have to start seeing it for what it truly is, a physical machine embedded in our spacetime that is literally in a battle with the fundamental geometry of our universe. Which leaves us with one last, pretty provocative question. As we keep pushing to build ever more powerful artificial intelligence, maybe the ultimate barrier we're going to face isn't a failure of our logic or our algorithms, but a fundamental, unavoidable limit imposed by the very shape of space itself.